Chapter 5, Objective Constraints and the Design Variables of ASTROS. ASTROS finite element discipline is a next-gen based for which most input cards for structural modeling are similar to those in MSc next-gen. Only the property cards for plate, bar, rod element, as well as the concentrate masses and spring elements can be selected as design variables. The solid 3D element cannot be defined as design variable. Both metal and composite material can be modeled, and global design variable can be linked via physical link or shape function link capability. That means so-called physical design variable, or also so-called local design variable ASD. For example, the thickness of the plate element is a local design variable. Then we can link a set of the plate element together to define as a global design variable, or we can define the thickness distribution of a set of a plate element by a set of shape functions. So rather the thickness of the element become a design variable, the coefficient of the shape function become a global design variable. An objective function in ASTROS, the default is to minimize the structural weight, or you can define a synthetic function of the structural responses or characteristics of the finite element model as objective function. Synthetic functions are available in ASTROS to play the role of either the objective function or a constraint function. Synthetic functions are formed as a mathematical combination of analytical responses such as stress, factor rules, model characteristics such as weight and thickness. For example, you can specify optimize objective function. The default is weight, or you can refer to dconf car, okay, to define a synthetic function. The ASTROS defines design variable at two levels. The first one is called physical or local variable. Another one is a global design variable. So-called local design variable is for example, the thickness of the plate element. A global design variable is just link a set of elements to become one design variable. And the basic rationale for having those two levels is to reduce the number of design variables to a number that is tractable in a mathematical programming context. If you have too many design variables in the gradient-based optimization, the sensitivity of the objective function or constraint function become less accurate because you have too many design variables. So we have to reduce the number of design variables as much as we can. Also provide the user with the means of imposing constraints on the design tasks that are desirable due to manufacturing or other constraints. For example, if we want the thickness distribution of a set of a plate element to model the wind skin to be smooth, you can use the so-called shape function, and to ensure that the optimized thickness distribution to be smooth. Okay, the physical design variable or the local design variable, the element is C rod, the property card is P rod, so the area of the rod is a design variable. Or C shear or P shear, the thickness of the shear element becomes a design variable. And for C quad 4, C quad 3, you can refer to P shell car or P com car. So the membrane bending or the composite layer thickness can be selected as a design variable. C bar, you have P bar and P bar 1 and P bar ST. and the area of the P bar become a design variable. All the cross-section parameters to define the defined in the P bar 1 can be selected as a design variable. Or P bar ST for composite stiffener, you can select a layer or a set of a layer in those become car to be a design variable. For Conam 2 is the mass. C elas 1 or 2 is the stiffness, and C mass 1 and 2 is the mass. Design variable linking, and we have three cards you can be used to define a design variable. The first one called DSELM. This is a unique physical design variable, meaning each DSELM refers to ID of a C-quad, C-quad, or bar element. So this is a unique physical design variable. And the second one is called Desva P. It refers to the set of property cards of a set of elements. Okay, so you can link them together to become one design variable. Desva S link shape functions design variable. So rather than you can define a set of a shape function to describe the thickness distribution over a set of plate element. So the coefficient of those shape design variable becomes the coefficient of those shape functions become design variables. And how to link them together? If you use Desva P, you can use either E-list or E-list M to link the element ID, okay, of a set of element together to become one the design variable, or you can link the property card of a set of elements to become one design variable. And if you use Desva S, you refer to a shape. In the shape, you define the shape function, okay, and a set of shape functions. So each Desva S refers to the coefficients of this shape function. So DSELM, you define ID, and you refer to element ID. E-type you can be one of those elements, and V-min and V-max is the minimum and maximum allowable of the design variable. V-init is the initial value of the design variable, and layer number, the layer number of a composite element to be designed, and the label is you use a supplied label to define the design variable, and DVSYMBL it depends on what kind of element you choose. If you choose the plate element, then this guy must be T. And that's why P links a set of property cards to all elements to one design variable. So you have the ID for this design variable, and you can link ID refer to the either E-list M, P-list, or P-list M. So in the E-list and E-list M, you refer to the element ID, a set of element. You list out a set of element IDs. P-list and P-list M list a set of a property card ID. Again, V-min, V-max is the minimum and the maximum allowable. V-init is initial guess, and layer number is you refer to a single layer of the composite element if the property card is a P-com card, or you can refer to a ply list. You can specify a set of a composite layer to be linked. So we will give you an example later. And that's far as you give ID, and it refers to a ID of the shape car, and we don't use shape M, shape G car anymore. We only use shape. And again, V min, V max, the minimum and the maximum allowable. V init is the initial value of the design variable. Layer number is refers to a single layer, and the layer list is refers to the ID of apply list. In the apply list, you can list out a set of a layer index. So if you use a layer list, then you cannot use layer number. Okay. The BCOM car for defining the property of a 16-layer composite panel is usually shown as follows. Because the gradient-based optimizer cannot handle discrete design variable integer for number of plies, the design variable must be related to the thickness of each layer that has the same fiber direction. Since the stacking sequence may have impact on buckling constraint, the best stacking sequence is plus or minus 45 degrees and 0 and 90 symmetric. This is an example. If we have a layer of composite, because the composite laminate must be symmetric, so we want to link the top positive and negative 45, and the bottom positive 45 and negative 45 to be one design variable. So we first define applied list ID 1, 2, 3, 7, 8. So we link apply 1, 2, 7, 8 together, become one design variable. Then we define a Desva S, which we refer to the supply list. Okay, and then because layer 3, layer 6 are the 0 degree ply, and we link them together. We define another Desva S, which we refer to 3600. Okay, finally, layer 4 and layer 5, which is 90 degree, we have to we define another ply list with link 4 and 5 together, and we use another Desva S, which is referred to 4500, and so we have 3 design variables. So rather than we have 8 layers, now we reduce to 3 design variables. The constraint in ASTROS, we have a displacement constraint, and this displacement is driven by statics or S arrow. And you can impose this displacement constraint by dcon dsp, and it is activated by the solution control dcon equal to set. Set is a set ID of this dcon dsp. Buckling and crippling, you have dcon bk for panel buckling, dcon bke for column buckling, dcon crip for stiffness crippling constraint. Also is driven by statics or S arrow, and activated by dcon equals solution control command. And you can impose the natural frequency constraint. It's called dcon frq, and is driven by modes. Flutter is a dcon flt, and is driven by the flutter module, and also is activated by the dcon solution control command. Lift effectiveness is a dcon CLA. So the ratio becomes flexible, and the rigid must be greater or smaller than a certain value. This is driven by S arrow. Aileron effectiveness constraint, and it's defined by the negative rolling moment per control surface, and divided by roll rate, and it's driven by S arrow. And finally, we have a stiffness ratio constraint between stiffener and attached panels. This is called dcon KR to prevent whole stiffness panel bay buckling mode. And then for strength, we have a Laminate stress and defined by those cars, and it is driven by static or S arrow. It's activated by stress equals solution control command. Side stress, you can use those cars to define the side stress constraint. Also, it's driven by static or S arrow, activated by the stress equals solution control command. And this principal strain, you can use those cars to impose principal strain constraint, and it's activated by statics or S arrow. Is activated by the strain equal solution control. And for the fiber transverse strain, you can use those cars. Also, it is driven by statics or S arrow, activated by strain equals solution control command. And we have a manufacturing constraints. The first one is called decon length. Decon length requires the thickness of several plies in the laminate divided by the total thickness of the laminate must be greater or smaller than certain value. The reason of this is that this kind of constraint is not driven by any other discipline, because when we measure the property of laminate by performing the coupon test, well, then we cannot afford to do too many various thickness percentage. For example, we only can afford to do the coupon test of laminate, which has a 0 degree ply from 40% to 60%. So we only have those properties in our database. Therefore, for the optimized structure, we want the resulting laminate, the 0 ply thickness in the total thickness within 40 and 60%. Okay, so this is a so-called decon length. And the decon LMN, laminate minimum gauge, and the ply minimum gauge is decon PMN, and the composite layer, the thickness decon thick 2, and the bar element cross section is decon thick 3, and thickness constraint is decon thick. The number of constraints of flutter, the sensitivity of flutter constraint is the number of constraints is the number of a decon car, and the number of sensitivity of constraint is the number of constraints times of the number of design variable, because each constraint will have to take the partial derivative with respect to each design variable. So the total number of sensitivity is the constraint times the number of design variable. However, the decon flutter, the flutter constraint is defined. First, we have a flutter car to define to perform a flutter analysis, and then we have say we have 20 modes. Then the flutter car refers to the fixed MDAN. In the fixed MDAN, we list out 1, 2, 3, 4, 5, 6, 7, 8 velocities. Then in the decon flat, we define, say, from 0 speed to 217 speed, the damping must be less than 0. Okay, so at each velocity will give us 20 damping value. because we have 20 modes. So the total constraint is 1, 2, 3, 4, 5, 6. 6 times 20. So the total damping value is 20 times 8. But the velocity below 217 is only 6. So the constraint is 120. So the number of flutter constraint sensitivity is 120 times number of design variable. Therefore, to reduce the number of flutter constraint, it is recommended that only a few velocities listed in those fixed MDAM, fixed ATM, fixed mark car. This slide shows the failure modes of stiffened panel bay. Impose panel buckling, crippling, column buckling, stress strain, and a stiffness ratio constraint altogether can lead to an optimum buckling mode in which the stiffener panel between stiffness and the whole stiffening panel bay buckle together. The optimized stiffened panel bay is a minimum weight design. So the first is the inter-river buckling, or this can be constrained by decon crib, and this is stiffened material failure. You can impose the stress and strain constraint, and if the whole stiffened buckle, you can impose so-called column buckling. Or within each panel, within two stiffener, the panel buckles, we can impose the panel buckling constraint using decon BK. And for the stiffener crippling constraint, we can impose decon CRP. To prevent the whole stiffener panel bay buckle, we can use the decon KR, the stiffness ratio constraint. The buckling loads are generated by the SRO or static case control command, and the buckling constraint of the plate element is solved by the Glerkin method of a simply support plate. The buckling constraint of the bar element is solved by the Euler buckling equation. So if we specify SRO, then SRO will induce loads. So due to the trim analysis, and under this load, we impose the panel buckling constraint and column buckling constraint, and so in the standard output file, the buckling constraint value at least as below. It tells you what the constraint counts, the value, constraint type, the boundary condition, the case, the sub case, what kind of element, and element ID. And decon BK is to impose the panel buckling constraint, and you give ID, then you select the type of a plate element, either quad 4 or chart 3, and the element ID, and the length of the panel, and the width of the panel. Boundary condition, you have a SS for simply supported, and SF for simply supported with one edge free, and FF for simply supported with two edge free. And the C type is lower, or we have other option, and the buckling limit, the default is 1. And the buckling constraint is activated by the decon case control command, and the buckling control element and supplies the running loads NX, NY, NXY, and mature property to the rectangular pseudo panel of dimension length time width. Okay, nx, ny, nxy, the running loads are induced by either S arrow or static. If the length and width are not input, the corresponding value will be computed from the rectangles that of the control element. Okay, and so we have many different ways to define this panel buckling constraint. And the decom BKE is to define an order buckling constraint or column buckling constraint. Again, this is the buckling constraint ID. E type either is bar or rod, and element ID and the length of the bar and rod. BC type is the boundary condition, and C type either lower or upper buckling constraint value, and shear meaning if you impose the shear force or not, so either yes or no, and RSQR parameters which defines the inertial link when E type is the rod element. So if you have a rod bar element, because in the bar and the rod element we only give the in the rod element we only give the area. So how do we define the inertia? And we use this equation to define the inertia. Decomcrip is to impose composite stiffness crippling constraint, and so it refers to a C bar element and with ID. And however, this C bar car must refer to a P bar ST car. The length is the length of the stiffener, and DI because in the P bar ST we can define a flange or web. Okay, so you have one web. You may have a two. You may have a flange and web. So D1, D2, D3. If you look at P bar ST, is the width of each flange and web. So you want to impose the crippling constraint to which flange or web of this P bar ST. If you say DI say equal to R, or that you impose the column stiffness crippling stress constraint. Okay, and C type is lower or upper, and lambda required is a crippling constraint value. Default is 1, and EFC ultimate compressive strength limit in the fiber direction. EFC is used only if DI equals R. So the crippling constraint is activated by decom equals string control command. If the length is omitted, then the corresponding value will be computed from the length of the C bar. And the stiffness specified in the P bar ST consists of a flange and several webs. Each flange or web can be considered to be a composite panel, except that it may be it may have one edge free or no edge free. Assuming the length of the panel specified entry length, referred to as A, is much smaller. It is much larger than the width. D1, D2, D3 specified in the P bar ST car, referred to as B. The equation to compute the critical buckling load is shown as follows. So with no edge free, one edge free, the crippling stress is computed by this equation, and T is the thickness of the flange or web. The crippling buckling stress is defined by lambda, so sigma CR divided by sigma. Sigma is the running load. And we have other ways to define the column stiffness, crippling stress constraint, and so on. Okay. An important note is that if you have several panels surrounded by constrained by stiffness, rib, or spot. So if we want to impose the buckling constraint of those plate elements, the length and the width must be the whole length and the length width of the whole stiffening panel bay. Okay, not the length and width of individual elements. Likewise, if you want to impose the column buckling constraint on the stiffener, the length must be the length of the whole stiffener panel bay. Another one is that so if you have we have another constraint called stiffness ratio constraint for preventing global panel buckle. Okay, and to prevent this panel local skin panel buckle, we have decon BK. To prevent the stiffener we have a buckle, we have a decon BKE, and we to prevent the stiffener crippling constraint, we have decon crip. However, this is one panel buckling mode, which those constraints cannot consider, is the whole panel bay buckle. Okay, to prevent the whole panel bay buckle, we have to use the so-called stiffness ratio constraint, the ratio between the stiffener and its attached wind skin, and this is defined by decon KR. So we have a stiffener, we have a skin panel, and we have to define the stiffness ratio between the stiffener and attached skin panel. Okay, we talk about this one later. Okay, so before we talk about decon KR, let's look at this called K ratio, evaluation of a stiffness ratio. This is not a constraint. This is just an analysis. Okay, you give an ID, you give a file name on which the P bar, PBRC property car for of those C bar elements that does not satisfy the stiffness ratio requirement are punched. Okay. So you give lower and upper. If the stiffness ratio is does not satisfy this constraint, those P bar and P bar SC will be punched in this file. We have three different methods to evaluate the stiffness constraint. Let's look. Okay, and the width. If method equals 0, width is the width of the stiffener modeled by the C bar element. If method equals 2 or 3, width is the distance between stiffeners on the stiffening panel bay, and A is the length of the stiffening panel bay, B is the width of the stiffening panel bay, and PB is a post buckling factor, and ID bar. Okay, let's look at this. ID bar. ID bar is the ID of the C bar element. And L plate is the ID of the C4 C3. That is attached to the left hand side of the C bar. And R plate is the ID of the C quad and C on the right hand side of the C bar. and so ABM, either ABM or DI, the D1, and lower bound and upper bound. Okay, and so let's look at if a method equals 0 or 1, and the EA is the equivalent uh, 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 the, uh, the equivalent Young's let me see. Oh, EA and EA is the Young's equivalent Young's modulus times the area of the stiffener, and the ETL and ETR is the equivalent Young's modulus times the thickness of the left hand side, left and right hand side, sigma 4, sigma 3 elements. Okay, so this defines the stiffness ratio between the stiffener and the attached plate elements. If method is 2, we use this equation, or method 3, we use this equation. Okay. So those P bar, ST both are referred to by C bar element whose stiffness ratio is not within the limit specified in the lower and upper are punched on the file. Okay. The figure below shows a stiffened panel bay with a size A and B, and ds is the distance between two stiffeners, which define the width. Okay, so imposing method 2 for stiffness ratio constraint on this stiffening panel bay can lead to the optimum buckling failure mode, of which the panel between two stiffeners and whose stiffening panel bay buckle simultaneously. So the this option ABM, if it's A, that means you select the length, the XLR is half of this length. If it's a B, it is the half of this length, half of that length. If it's a M, it is in the middle. If ABM equal to D1, then the D1 specified in the P bar ST car is used, and so those two values is D1 divided by 2. If method 2 or 3, and the ds is used as the width. Okay. So after we introduce the K ratio, then we can talk about the stiffness ratio constraint. So, and the C type is either upper or lower. K required is the minimum or maximum stiffness ratio, and ID bar is ID of a C bar element, whose actual stiffness EI or bending stiffness EI is used to evaluate the stiffness constraint. AB is the same is the AB entry of the KR ratio, and L play and R play is the same as the one defined in the K ratio. And method is we already talked about that. Width is look at the entry width in the K ratio. A, B, and PB are all shown have been shown in the K ratio card. Okay. The next one is kind of a it's a composite laminate composition constraint. As I mentioned previously, we want to say we in our database, if we only have the coupon test result of say 0 degree ply is 40% to 60% of the total thickness of the coupon. And then we want to optimize structure. Also, the 0 degree must be within 40% and 60% as an example. So this constraint is not driven by any discipline. Okay, so constraint type either upper or lower, and this one percentage required a minimum or maximum percentage of the total laminate thickness that is to be made up of the ply thickness. Ply number, you can refer to a single ply, or you can refer to a ply list, and then those layers, the thickness of those layers add together must be divided by lambda, the T lambda, the total thickness of the laminate must be greater than or smaller than the upper and the lower bound. And that's when you refer to the called element list. You list a set of a composite element to which the composition constraint will be applied. Okay, to define a decon lamp, only one of either ply number or ply set can be used. If the element lists a car with a set ID listed the C bar, that refers to the P bar ST car. The layer number listed in the P ply number or ply list car must be within 1, and the total number of the PCON 1, PCON 2 car. Let me give you one example. If the P bar ST refer to PCON cars of the number of composite layer of the first, second, and third PCON car are 4A6. So the first PCON car has 4 layers, second PCON car has 8 layers, and third PCON car has 6 layers. So the total number is 18. If you define, say, the ply number equal to 5, it refers to the first layer of the second PCON car. Okay. In addition, the layer number listed in the ply number or ply set are those listed in the entry length must be belong to the same PCON car. Okay. The definition of ply and laminate thickness can vary from one entry to entry. Ply number is used to define the T ply that one layer constitutes a ply. Otherwise, T ply is the sum of the layer thickness of all layers listed in the ply set. Okay.